Welcome everybody for attending today's presentation on addressing ISO 26262 compliance testing for automotive software. I am real thankful that Arthur Haken is here, our chief evangelist. He's a brilliant mind and a good friend, and so thank you, Arthur, for joining me. Anyways, let's go to the agenda. On the agenda, I'm going to start with a very quick and high-level introduction of the standard. I will also be mapping verification methods defined in the standard to Parasoft solutions, which static analysis is one of them, and Arthur is going to kick us off on that topic. I also might have to race through unit testing, structural code coverage, and requirements traceability, which are the other testing methods recommended by the standard. All right, so let's get started. To give you a little history, ISO 26262 is created from IEC 61508 for the automotive industry. IEC 61508 is a basic functional industry safety standard for electrical, electronics, and programmable electronic devices, which is applicable to all kinds of industries. So by inheritance, ISO 26262 is a functional safety standard. It provides guidance for regulating the entire product lifecycle at the software and hardware level, from conceptual development all the way through to decommissioning. Now, other standards like IEC 62304 for medical and EN 50128 railway have also been derived from IEC 61508. And there's actually other standards as well, like 61511 for machinery and so forth. Okay, but let's now dive into the parts of the standard. Let's go to the next slide here. Okay, so you can see now the latest ISO 26262 2018 is divided or subdivided into 12 parts. The standard has been evolving since its first edition released back in 2011. Now I'm going to start with the most current adaptations. Part 11 is the adaptation of functional safety guidelines for semiconductors for automotive. It offers guidance and information to semiconductor manufacturers on how to develop compliant IP to the standard. It helps incorporate functional safety because users of semiconductors may not know how to use the semiconductor safely. And this has all evolved because automotive systems have become very complex, and semiconductors have enabled most of the recent innovations, which includes vision-based technology, enhanced graphic processing units, GPUs, sensors, DRAMs, and other components that empower advanced driver assistance systems, or ADAS. Now, part 12 is actually for motorcycles. And I actually enjoy motorcycles. In my younger years, I used to actually recklessly ride a Ninja Kawasaki 600. But when I got married, I had to let my iron horse go. A sad moment, but probably a life-saving one. So anyway, so that adaptation is for motorcycles. I'm not going to talk too much about that. So now what I'm going to do is I'm going to dive into the other 10 parts of the standard by way of the ISO 26262 overview diagram that you see actually on the right-hand side there. So this is straight out of the standard. Now, at the very top, you have part 1, which is the vocabulary section, so terms and definitions. Now, part 2 is about establishing an internal functional safety process for the team or organization that oversees the planning, coordinating, and documentation activities related to functional safety so that you're ensuring compliance. Now, this is of utmost importance because the development of safety critical automotive systems is really, really important because lives depend on it, especially now with the introduction of driver assist and automated driving systems. Now, part 3 is the concept phase, defining what you are building and where your customer or stakeholder requirements come in. You will notice on the right side of that little box there, the beginning of a gray shaded V watermark. The shaded V represents the interconnection among parts 3, 4, 5, 6, and 7. Now, these series or parts of the standard are based upon a V reference process model for the different phases of product development. So actually, I'm going to kind of dive into that. Part 4 is the beginning of product development at the system level, which has various phases, right? At a high level, they are comprised of requirements decomposition, design, implementation, and testing. Now, these phases have been partitioned into 2 domains, Part 5 for development of hardware and Part 6 for development of software. So I'm going to dive actually into the software aspects of it. So you can see in there the lighter gray V watermark for software development. And again, the left-hand side of the V encapsulates the requirements decomposition, design, and implementation phases. And on the right-hand side of the V, section 6.9, 10, and 11 represent the testing or verification and validation of the software. This includes unit testing, static analysis, structural code coverage, requirements traceability, and actually more. But you'll notice that those are the topics that I've chosen for this presentation. Anyways, but let's complete the workflow. Now, Part 7 addresses the production and operation, which means the product is out in the field and you have to consider things like maintenance, repair, and also sunsetting of your product, or referred to as decommissioning. Now, Part 8 specifies the various supporting processes in the development of the system that help ensure functional safety. These include having various specifications in place, including solutions like configuration management. And one other actually very important aspect of Part 8 is the qualification of the software tool that's being used. You don't want to use a tool that has not been certified, which can actually undermine the safety or security of your product by actually introducing issues. Now, Part 9 is a critical section to understand because it pertains to assigning a risk classification on the system or component that you're developing. This means that you have to take into consideration the risk to the passengers, the pedestrians, if the electrical or electronic systems were to malfunction or fail. And I'll go into this actually a little more detail on the next slide. But to conclude this infographic, Part 10 basically provides an overview of the standard with additional explanations that enhance the understanding and concepts of the other parts. So it's considered to be very informative. Now, ISO 26262 is a risk, again, based safety standard. When the risk of hazardous operational situations, it needs to be assessed. And so the safety measures need to be defined and to detect and avoid or control failures. This needs to be done because you need to mitigate or take some actions regarding, what happens if it fails. Now, when the hazard analysis and risk assessment is performed, the automotive system or component under development, an automotive safety integrity level, ASIL is what it's referred to, a certain level is assigned. And so you have levels A through D, level A representing the lowest hazard assignment and level D representing the highest hazard assignment, meaning that the failure of a system or component with ASIL D could be catastrophic. So you may also, if you notice on the slide, there's a quality management level. If you happen to see a QM in certain documentation, this means that there is no safety requirement. So that may also show up in some document. Now, ASIL can be determined and assigned by taking the severity. And you can see in this table that there are several severity levels of injury. And so you take that, then times the probability of the failure times the controllability, and you'll get your ASIL. Now, to be more specific, severity represents what would be the impact or damage if the failure occurred. Exposure represents the frequency or probability that the failure would occur. And controllability is the extent to which we can ensure that the event doesn't happen. But better yet, there are several tables out there, and let's take actually a look at one of those. This is an example where it's very easy to read, and you can see the ASIL levels and the colors based on severity, exposure, and controllability. Now, this slide captures some of the safety systems that I've been referring to that may come with a roadside vehicle. You are also seeing some of the ASO levels assigned. Now, some of these safety systems are considered active safety and others passive safety. Active safety is used to refer to technology assisting in the prevention of a crash or accident. So you have, for example, your traction control and your anti-lock braking systems and others. And then you have passive safety systems, which are meant to keep the passenger safe in case of a crash. So you'll have your airbags and seatbelts. So now that we have gone through a very quick introduction of the standard, I'm going to focus on part 6. This means that we need to understand the test verification validation methods recommended by the standard and be compliant. So I pulled some of the tables from the standard. For example, table 9 captures verification methods during design and implementation, like static code analysis. On the right column, you'll see a symbol representing the type and strength of the recommendation based on the ASO level. And the plus, the single plus means recommended. 2 pluses means highly recommended. And the O or 0 means that there is no recommendation. Now, table 10 captures verification methods for unit testing. Table 11 captures methods for deriving unit tests, such as analysis of boundary values. And there's a list of others as well. Table 12 lists the recommended structural code coverage metrics to ensure test coverage. So the standard defines a lot of testing methods to consider, and you should look for a solution that helps address these needs. So at the end of the day, you need to satisfy the test verification and validation methods recommended by the ISO 26262 standard. So you need a solid tube certified test automation solution, which Parasoft tooling has been tube suit certified for use in all ASO levels, A through D. And our tool solution expedites your testing efforts. It reduces the amount of labor and boosts your productivity. Parasoft has actually also employed AI and machine learning to help our customers with these pain points that go beyond your traditional just test automation. Anyways, in this V diagram, you can see our list of products to the right that address each of the various bases for verification and validations defined in the standard. And you can see a list of methods on the bottom right. You can see those under the verification and validation. Lots of methods there that we support. I also want to mention our seamless adoption. Parasoft is a test solution that plugs right into your development ecosystem, such as your engineers integrated development environment, or IDE. This means that using our solutions will be intuitive, so very, very short learning curve. And our solutions work with numerous compilers, real-time operating systems, and you can perform your testing on the host or the target hardware for your validation needs. And for today's connected cars, we offer testing solutions that leverage virtual services, API testing, application coverage, and other technologies that address the challenges in testing connected platforms. And on the left-hand side of the V, you can see our DTP solution that provides the integration with requirements management tools for requirements traceability to test and also all the way down the code. Now, okay, starting with the implementation phase, we're going to cover how folks out there in the real world are addressing the standard through static analysis. And my colleague, Arthur Hicken, is going to start us off. So over to you, Arthur.
All right, thanks, Ricardo. Yeah, so it's pretty interesting. We've been looking at different surveys that are out there, like the Bar Group, and say, what are people actually doing in the embedded space to make sure that software is both safe and secure, as well as well built? And we see here the last survey they did was 2018, and we can see 2017 versus 2018. Coding standards, obviously a practice people do, peer code reviews, static code analysis, and standards without static code analysis. Now, it's kind of funny because the dark blue bar makes it appear as if people are doing less coding standards in 2018 than 2017. But in 2018, they actually add 2 categories. One is, we do this thing, but it's not enforced. So it's an optional practice. So there's actually more coding standards going on in 2018 if you add that dark blue and the green bar together. But it's kind of funny because if you're doing standards that are not enforced, it seems kind of odd in a functional safety space. And in particular, that chart on the right, the standards without static, if you're not using static code analysis to enforce your standard, I guess that means it's all peer review. Boy, that's just not sustainable. In the days when we had 100, 200 lines of code in an emissions control system, you could certainly do that. In fact, it was the right answer. But with today's, connected cars and all these active safety systems, steering systems, control systems, even the climate control system is incredibly complex. We have tens, if not 100 million lines of code, and we really need to use tools to do that as much as possible. The other interesting message that we see here over the last several years is that C and C++ are not just still alive and being used, but they're thriving in the embedded space. We tend to see C used more at the smaller device level where there's less code, and C++ where the device itself, the system, the component, requires greater logic to it, greater capabilities to it. So there are definitely things, don't worry about using them. They're still live, vibrant languages today. We also like to take a look at what are the standards people are actually using. And this is kind of surprising to me because what we see is that still proprietary coding standards are a real strong thing being used. MISRA, it's there, it's growing. We have a couple other things, especially around modern C and C++, modern C++ really. And we'll talk about that in a minute, like high integrity C, etc. But not everybody is using standards like MISRA. And again, not everybody's using a written standard. And I'm not certain what the standard means if it's not written. And I guess the reason I point that out is that if you want to be safe and you want to do it consistently in a predictable manner, you need to use a coding standard. And 20 years ago, 25 years ago, 30 years ago, I saw a lot of companies that literally just had to build their own coding standard. Today, we have some really great solutions out there. In particular, we're going to look today a little deeper with MISRA and CERT because they're both just really great, well-adopted standards. The other thing I like to talk about is what I call the Death Star effect. In a modern vehicle, everything is connected. I have a 57-year-old car sitting out in front of my house, and the headlights are wired directly to a switch on the dash, and they don't connect to anything else. Everything is directly connected to the thing that it's supposed to be part of. And now we have this much bigger system. And with the Death Star in Star Wars, you had this huge monolithic flying device that would house people. And it has this one little tiny, who cares about it? It's such a little weakness. It's okay. We can protect the entire system. A failure, a security or safety issue won't really affect us. And what we see from MIT Technology Review is we know that everything is interconnected today. Like I was saying, my headlights on my newer car are connected into the bus. My air conditioner is connected into the bus. My transmission's connected into the bus. My emissions control system is connected into the bus and connected do things like the transmission and steering and things like that. And the point is that this makes risk much, much greater because a tiny thing can often lead to a much bigger problem like we saw with the Death Star, right? Catastrophic results at a whole entire system level. So if we look at a vehicle at a basic of different kinds of subsystems, we have, batteries, we have engine and other parts of the drivetrain, dashboards, which themselves are incredibly complex. I don't know the details of the dashboard of my current car. My previous one, they told me at the repair shop there was 3 computers there. One was the steering wheel itself. So a very complex system, steering systems, braking systems. And braking systems are kind of interesting because they've been around for a long time. We've had brakes as long as we've had cars, and we've had powered braking systems for nearly as long. So this is a diagrammatic view of a typical kind of a simplistic braking system, right? We have a power booster up on the top center leading through the system, and eventually you have lines leading down to the individual wheels so that you can actually, for example, in the case of a disc brake, squeeze the caliper and cause the vehicle to slow down. But little tiny things in this big system can cause big problems. We look at that hose in the top picture. It's a beautiful hose. It's got a beautiful metal protector on it. It's carefully routed. We look at the hose in the bottom picture, and it's cracked. It's got a pretty severe angle in it. It looks like a non-standard part. I had an interesting story I was telling Ricardo. I used to live in Chicago and had a car whose brake line looked exactly like the one in the lower picture. The line itself, when it had been last replaced, and I don't know when that was, I bought it used for not very much money, the brake line was wrapped too severely around the shock absorber. And so what happened is that as the brake line became brittle and cracked, one day when I went to turn the wheel and the entire unit turns and shifts and it puts tension on that line, it sprang loose. And in that case of that older vehicle, the entire braking system failed. I had no way to stop the car and had to drive into a snowbank. This big, complex, expensive system all failed because of this little tiny rubber part. So that's what happens. And that's the point around using standards to build things. I know that if you've come from the hardware side of the world, you often feel like the software people are just a little insane, maybe. They do things that seem chaotic, disorganized, and the point about coding standards, the MISRA guidelines, for example, is to not use pieces of the language that are unsafe and to make sure that we avoid pitfalls that we know can cause problems. So the role of static analysis and standards isn't so much to find bugs early or to test more, but to build a better product in the first place. And we know that when we're building things like vehicles, the goal of standards on the hardware side is to keep from building a vehicle like this. This is not my car, it's Ricardo's. No, I'm just kidding. It's not Ricardo. It might be, I don't know. But the standards tell you how things must be built, what kind of frame they have, etc. And that's the goal with software standards as well, to prevent some kind of a nasty thing from happening where you know that you've been hacked or you have a safety issue. And I like to talk about safety and security together. In fact, quality and reliability as well. It's really hard for me as a consumer to think that a car that failed to keep me safe or was easily hacked is a quality car or a reliable car. So they go hand in hand. And the interesting thing is that they literally do. In the C and C++ world in particular, we know that things like buffer overflow and memory abuse are the bane of everything. Safety, security, reliability, they're just always part of the problem. And the funny thing is, if you analyze normal defect information, you can actually begin to predict security and safety problems. So static analysis is really a key part of getting control of the software side of your automotive system. So let's look at one of those guidelines. There's the SEI, or Software Engineering Institute, as CERT Secure Coding Guideline. And it's really cool because, you know, we've talked earlier about ISO and IEC standards, and they cost money. And CERT's neat because it's freely available. And in fact, you can get involved there. You can help make changes, minor improvements, suggest missing items and things like that. The thing I like about CERT standard is that it's focused a lot on engineering and prevention, or on the things that cause problems rather than on the symptomatic bugs that occur. So it's really great. It does have specific implementations for different languages, so it has very interesting information for the languages C, C++, Java, Perl, Android, etc. It's got a couple different categories. We'll look at those in a moment, and ways to score things. I do want to point out, if you don't like using it, it is a wiki. So you go to a web page and you peel through it. They do have a PDF download, but recognize that the PDF is sporadically, not on any regular basis, produced into from the wiki into a PDF and released. The last time they did that was 2016. So I would say when you're looking for tools for CERT, just keep in mind that some people advertise that they support the 2016 standard. the 2016 standard is not the current standard. The Secure Coding Wiki is the current standard. So make sure that you're up to date with whatever you're using. So as I mentioned, there's two types of guidelines in CERT. We'll see something very similar with MISRA. Some of them are required because the defect that may occur is likely to have some kind of a safety, reliability, security system and doesn't rely on assumptions or annotations. In other words, we can get a good decision from the software that's an objective decision. And we can do that through automated analysis or formal methods or manual inspection. So we can be really sure it's followed. That's the idea. And the recommended ones are either less risky, less dangerous, or they're simply the kind of a thing that we can't really get a binary decision from a tool on. So it's interesting because when you're getting started, you might want to pay more attention to the required ones. I know that not everybody has bothered to sit down and read a standard, and like reading ISO 26262 can be a bit of a slog if you're not used to it. And CERT similarly can be that way as well. So I wanted to just cover quickly what you're seeing when you pull up the CERT wiki or when you pull up the PDF. So we get the name or title of the individual guideline. We get some normative text that tell us what it's really about. So that's very helpful. Then we get two different examples. Sometimes there's a lot more than two, but a minimum two. One is the non-compliant code. This is the bad code. This is how you don't want your code to look. This is the anti-pattern. And then we get compliant code that won't have the problem. So it's great. You can see what both things look like. We also get other guidelines that are related to this. And this is interesting because, again, there are lots of standards out there, the BAR, the High Integrity C, the CWE, CERT, MISRA, etc. And so CERT actually shows you, hey, this particular guideline also shows up over in ISO 17961 or CWE. And so you can go look at other standards or maybe get more information about it. So that can be helpful in trying to understand something. And then CERT has this nifty thing about risk assessment. So similar to what we looked at with ASIL, where we had things like exposure and severity, we have severity, we have likelihood, so, probability that it can happen, and remediation costs, which is a little different. With ISO 26262, remediation isn't what they use. They actually use controllability, meaning can the driver of the vehicle do something about it? Here with the remediation costs, we're looking at software. So we're saying, can I do something in the system that would prevent this from happening? And is it expensive? So this is great because it helps me understand how nasty something is, and I know what's most important and what's less important. And then they have a section at the bottom that shows you which tools can automatically detect this particular thing, so that you know when you're looking whether the tool that you're looking at is going to help you with this. Because any item in CERT that a tool doesn't look for, you have to look for by hand if it's a required guideline. So, and some of them only we support, as you see with this particular one. So I wanted to just dive into how they do this risk thing. They had those three categories, as I mentioned, and they basically give each item in each category a score of 1, 2, or 3 with a very objective set of standards. And that's what I love about it. It should mean that if I analyze something, or if Ricardo analyzes something, or if you analyze something, that we'll get the same kind of a score. And then they do just like 26262, you multiply them. You multiply them together, and the highest values are given a high severity, meaning it's likely to happen. It's a bad thing if it happens. And it's inexpensive to have avoided it in the first place. Whereas the green items, they're low severity. It doesn't matter as much if they happen. They're unlikely to happen, and making them not happen would cost you a lot of money. So you want to focus on the other part of the category. And they implement it like this cool target, so that you basically go to the red stuff and you find out the stuff that's, dangerous and likely to happen and cheap to work on. So just a quick, how does that look in the real world? Here's one of our dashboards that shows, compliance to a standard, and you see various categories and rules. We have a heat map showing you where the violations of the standards are, and we actually have that nifty little CERT target. One of the cool things that we do in static analysis that I did want to point out is that we use what I like to call a mapless implementation. So it means that if you're doing MISRA or CERT, you don't have to look at the Parasoft rule IDs or checker IDs and figure out, this Parasoft checker, how does it relate to CERT or how does it relate to MISRA? We actually rename the checkers so that they show up per the standard. So if you're looking at, MISRA 72-B, that's what our checker is called. If you're looking at CERT 27-C++, that's what our checker is called. And we use the actual risk frameworks from the standard. So we're a very standard-centric format, which makes a much easier thing. You don't have to figure out what checkers do I need to run, and you don't have to figure out during an audit, how can I demonstrate that I used the right checker, because it's always that way. You always know what you're working on. So it's really helpful to actually running the standards. So with that, Ricardo, let's talk about MISRA.
Okay, thank you, Arthur. Arthur, you notice that he lives a very interesting life, and I love all his examples and analogies. And thank you, Arthur. Okay, so I'm going to start with some interesting news about the MISRA consortium, in that they are celebrating their 25th year of publication. MISRA is known for its coding standard for C and C++, which is widely used not just in automotive, but in all industries: military, aerospace, industrial, rail, medical, and so forth. And the consortium members are comprised of not just automotive companies, but component suppliers, engineers, consultants, and members from other industries. And in fact, Parasoft happens to be an active member. Now, the current guidelines that contain recommendations for the use of the C language is MISRA C 2012, and there's actually an amendment too that has come out recently to update it. And the guidelines containing recommendations for the use of C++ language is MISRA C++ 2008, which is superseded by AUTOSAR C++ 14. So this actually leads me to the next slide. The Automotive Open System Architecture Organization, AUTOSAR, provides a set of specifications to standardize the development of a software architecture for electronic control units. And they define an adaptive platform that is developed in C++. So MISRA C++ 2008 is based on C03, which does not support critical safety-related software. Hence, AUTOSAR C++ 14 was created, and they have been releasing their C++ coding guidelines twice a year since March of 2017. So in January of last year, 2019, the two world-leading consortiums in C++ coding guidelines announced the integration of the standard into one publication. So the goal is to unify these two standards so they fully support C++ 17 and C++ 18. Now, MISRA uses the term guidelines, which can be broken down into a rule or a directive. And it's important to understand that directives differ from rules, in that directives may not be easily or possibly confirmed or checked for compliance. For example, there's Directive 4.1, which states that a runtime failure shall be minimized. Well, how do you check compliance for that? So the burden is actually placed on the developer to ensure that that directive is satisfied. Now, rules, they can be checked for compliance by looking at the code, by just simply checking. For example, MISRA Rule 17.3 states that a function shall not be declared implicitly, so I can, again, look at the code for that. In addition, every rule and directive will have a category field. For rules, the category field will contain the word mandatory, required, or advisory. And for directives, require or advisory is what you're going to be able to find. Now, I'm going to start with mandatory. If a code is found to violate a rule that has the mandatory value, the code must be fixed. There is no exceptions. Now, a required value permits a deviation. I'm going to talk about deviations. So, and you're going to need to provide a justification for that deviation. Now, an advisory value expresses a recommendation, but don't just go off and ignore these, because really they're very important. They're an accumulation of years of experience by members and engineers and the committee, so they're aware of some of these violations that you might find out that you should address. Now, the image on the right gives you a view of what a guideline looks like in the standard. So let's quickly talk about the deviations. The standard states that a deviation, which is an exception to the rule, can be defined and applied. So yes, MISRA does provide a suggestion how to capture these. And so you can provide the scope, location of where the deviations apply, provide a justification, including safety assurance for the deviation, and also provide the consequences and mitigations that have been taken into consideration. Now, in this code, you see here a switch statement that violates Rule 16.3. It states that every switch clause shall or must have an unconditional break. However, the developer wants to flow into case 1 from case 0, but this triggers the violation rule for 16.3. So just to recap a little bit here, to build safe, secure, and reliable code, just applying one type of testing will not catch all the issues. So that is why ISO 26262 recommends a variety of testing methods. We just covered static analysis, which is your first line of defense. Don't bypass that because that's really important. This is where you fix and find your defects early, and it's the cheapest to fix them. So what I'm going to do now is quickly go through the unit testing, structural code coverage, and requirements traceability, which are key methods to ensuring that all your requirements have been verified. So let's quickly continue to move up this verification and validation letter that's defined in the V process model. Now, unit testing is a way of testing a unit, which is like the smallest collective piece of functionality that can be logically isolated in a system. So in most programming languages, that boils down to a function, a procedure, or a method. Now, the purpose is to validate that each of these software units performs as expected, that these individual units are free of defects, and that they will fulfill the requirements that they're based from. Unit testing is very labor intensive because developers have to create many test cases to exercise that unit and flush out all of the defects. Then there's the maintaining and updating of the test cases when code changes occur. And from experience, I know that due to time crunches and reluctance from developers. I myself used to be one of them, and sometimes I wouldn't do it, and so it would fall upon the QA engineers to end up performing the unit testing. And to alleviate the labor and cut down the cost of unit testing, you will need to employ a test automation tool. So Parasoft raises the level of abstraction from code to a graphical editor so that you can seamlessly create, execute, and maintain your test cases. Better yet, Parasoft tools can automatically generate test cases for you, expediting the unit testing process, shortening the testing lifecycle, and giving you a huge labor cost savings, and also performing code coverage in parallel. You can do that to unit testing is another example of cost-cutting approaches here. Now, so Parasoft generates smart test cases. They test for many things like null pointers, divide by zero, boundary value testing, and there's a lot of other methods also that are recommended by ISO 26262 that we provide. And that's all to ensure the safety, security, and reliability of the code. Now, once you have all your test cases in place, in a complete automated test framework, the next version of iteration of software that you need to unit test can be performed for almost free. So be very aware of that. You get to reuse all the test cases, the test framework, and all you need to do is update it, create test cases where the code has changed, or add new test cases where new code was provided. And then you can perform your regression testing with as little as 1 or 2 engineers. So this is a huge savings. And I actually have done this in my past as a services project manager. But anyways, I got a little sidetracked with unit testing again. So going back to automatic test case generation, just imagine a tool that automatically generates test cases for you to find bugs and expedite the testing effort, lowering your labor cost while also delivering this high quality code. And an additional benefit is that these automated test cases can also fulfill your code coverage requirement. So let me dive into that. When you execute your test cases, And if you have code coverage enabled, one of the data metrics provided back to you is the lines of code that were not executed or covered. This is important because code that has not been executed has not been tested, so you have uncovered defects and gaps in your testing. Now, if you obtain code coverage through system testing and you have executed all of your system test cases, the coverage results will tell you how much of the code was executed. If only 40% or 60%, you have a lot more system test cases to create so you can reach more coverage. And since you can also obtain coverage through unit test cases, Parasoft has the capability to combine coverage results from both types of system or unit testing to help you get to the 100%. Now, if ISO 26262 were ever to get as strict as standard DO 178C level A for avionics software, Parasoft can also perform coverage at the assembly code level. So very powerful solutions that you have for the future. Now, real quickly, here, requirements traceability is recommended by ISO 26262 to help ensure that your requirements are tested and verified. The bottom graph illustrates an example of Parasoft keeping track of your testing methods and information like progress and health of your software. You see those pie charts there. That's our dashboard. And if you were to happen to click on one of those pie slices, what you would get is, for example, on the table there on the right, you see the requirements traceability. You see the requirements, and then you see that it traces to test cases and other artifacts such as source, and it even has code review information. Now, on that table on the far left, there is that key field, and that key column, if you click on that, it's a bidirectional connection to your requirements management tool where your requirements originated from, so it can navigate you to that particular tool. And then imagine if the top here, the ALM tool, the requirements management tool, Parasoft, as it performs its testing, it can actually propagate back to that originating tool the test results and test runs and other information as well, so that you can fill in whether it's been verified or not. Anyways, I better hurry up. We're running out of time, so I'm going to move over to the Q&A section. I hope that this presentation has been very informative, and to get more information, you can visit our website, request a product demonstration, and follow us on Twitter, YouTube, Facebook, LinkedIn, or send us an email at info@parasoft.com.